Alright, so this video is going to cover 12 through 23 on the outline, the concepts involved there. So first couple are pretty simple, and then we're going to get into some math, and then we're going to talk about the periodic table in detail. So states of matter are pretty simple. We've got solid, liquid, gas, and we've got AQ. So for that, you need to be familiar with those, but you also need to know on our particulate view what they look like, that the solid has the particles close packed together, that solids do not take the shape of their container or the volume. Liquids are still pretty closely packed together, but there's more random motion, more room for movement. The particles are a little farther apart so that liquids flow. Liquids will take the shape of their container but not the volume. And then gases, the particles are spread very far apart and they take the shape and the volume of their container. And then you do have to know that aqueous means that we've dissolved something in water. And so we've talked about recently that water will rip apart some chemicals and just surround others, whether it's able to break it apart or not. Okay. The separation techniques, you just have to be familiar with the types that we learned. So we learned 5 different techniques. So we learned filtration, and we haven't done all of these in lab yet, but we've talked about them. So filtration, that separates solids out of some kind of mixture. We talked about distillation, which is when you boil one component of the mixture away, or to separate them. So if you imagine salt water and you boil off the water, you're left with the salt. But they do this for desalinization. You can capture that water that was boiled, and then you'd have water without salt in it anymore. Okay. You have crystallization, which is a little bit what we talked about when we talked about rock candy this last week, about how if you give something the solid, a particle to form a solid on, it will crystallize out of solution. So like sugar, how it crystallizes on the string out of the solution when you first make rock candy. We had extraction, which is essentially what would happen if you had to separate oil and water. It's literally pulling one part of it out. So there's different devices for that in the lab, but you could just, if you imagine water and oil together, you would have a layer of water and a layer of oil on top. And so if you wanted to extract, you could simply pull out the top with a turkey baster or a pipette or something like that. And then the last one is the one we actually did in lab, was chromatography. And that's where we separated out the colors in that mixture, but how we separated them was based on whether they liked the water better or they liked the paper better. So just being familiar with what those were, recognizing which ones we talked about. Okay, so next thing up is your laws of matter. So you had 3 laws of matter, and we only really used 2 of them in practice. One was just to demonstrate that something actually is true. Okay, but we had the conservation of mass and definite composition. So conservation of mass says if you start with a certain amount of mass, regardless of what form it's in, you've got to end with that amount of mass. And then definite composition said, hey, if you have a particular compound, no matter where you get it from, it will always have the same formula. It will have the same proportion of masses in it. So we have some examples on that. Question number 5 on your in-class review says, all right, we've got 42.03 grams of nitrogen reacting with hydrogen to form 51 grams of ammonia. So at this point, you could probably write the chemical reaction of what's happening, but when we learned this, we weren't quite there. So what this is telling us is nitrogen is reacting with hydrogen to make ammonia. Okay, so now hopefully you would write that nitrogen is N2 and hydrogen is H2, and you may or may not know what ammonia is at this point, but it's NH3. Okay, but this is not, you don't actually need that equation or need it to balance or anything to answer this question. It says we've got 42.03 grams of the nitrogen reacting with hydrogen, and it's going to make 51.10 grams of ammonia. Well, it says what mass of hydrogen must have reacted, so this is simply a missing piece. We've got to have equal masses on both sides. So to find out the mass of hydrogen, we take 51.10 minus 42.03. and we get 9.07, and that is correct significant figures because we're doing decimal places. Okay, and we put grams, and the question after said, okay, what law of matter does this demonstrate? So this is the conservation of mass. Whatever mass we started with, we're going to end with. Okay, and then B says, what is the mass percent of nitrogen and ammonia? And so you could do this a couple different ways, and this is to kind of show you that it's going to be the same every time. So if you just simply use the masses given, you can do the mass percent is 42.03 grams of nitrogen over the 51.1 grams of ammonia. So remember, a percent is always a part over a whole times 100. And so if you do 42.03 divided by 51.10 multiplied by 100, you will get 82.25%. If you went instead to the periodic table and you happen to know the formula for ammonia, you could look this up, and we had to do this as well when I just gave you the formula. Okay, and you would say, okay, from the periodic table we have one nitrogen, which weighs 14.01, and the whole ammonia, if you add up all those numbers from the periodic table, we get 17.034. Okay, and if we did that calculation instead, you get 82.25%. So that's what the law of definite composition says. It says no matter what form or how much of it you have, it will always be the same percentage of each chemical. So that's the definite composition law. Okay, so next up was the development of the atomic theory. So number 6 on your take-home asked you about the scientists. I will not be asking you for the names of the scientists, but I do want to go over them, and more importantly talk about the order in which they discovered the parts of the atom. So this has all been done in the last roughly 100, 115, 120 years that we've discovered this. So the electron, discovering the electron was two people, really. Okay, I'm not going to ask you to quote these names, but we've got Thomson and Millikan, and one found the mass to charge ratio and one found the charge so that we could calculate the mass of this darn thing. Okay, the nucleus was discovered by Ernest Rutherford, and that was the gold foil experiment where he shot positive particles at this atom and saw that some of them would bounce back, and that's how we inferred that there was a solid or there was a positive center in the middle that was rejecting or repelling these positive things. Okay, and then the neutron was a guy named Chadwick, and that came from, hey, we're missing some mass. But I need you to generally know how we discovered the atom, what we think of it today, that about 200 years ago we had just a simple sphere. We thought that was the atom. And then they came up with a plum pudding model because they discovered there was negative particles in there. So they said, oh, we've got negative particles in this positive C. And then we discovered that, hey, wait, all the positives are not just in a little ocean there. Positives are all located right in the middle, and then we've got these negatives around there. Okay, and then we came up with what's called the Bohr model, where we said, okay, the electrons are orbiting around the nucleus like planets in our solar system. And so that's not quite where we're at right now. Where we're at right now is the electron cloud model, where it looks almost a little chaotic. But we're going to talk about in the spring how this is actually secretly organized. But the electron cloud, where we're not sure exactly where they are on little orbits, but they're in what we are going to call orbitals later this year. So just general development of the atom there. All right, so next up is atomic number, mass number, electrons, protons, and neutrons. So that's number 7. You have to be able to tell this from the periodic table. So we're going to go reference the periodic table, but I want you to keep this in mind. So we've got the 31, P, and -3. Okay, so if we come over to the periodic table, the thing you have to know about the periodic table, these values that are on here, so if we just take phosphorus that we're looking at right now, you have to know that this 15 is what's called the atomic number, but it's the number of protons. Okay, and then we have the symbol, the name, and then this right here is average atomic mass. It is not the protons, it is not the neutrons, it is not the electrons, it's the average atomic mass, which we'll talk about on number 17 on your outline. But what you have to get through on this is if I gave you that symbol, you have to know what's on there. So the number that you may have been given earlier this year, it was down here. That 15 that's sitting on the periodic table, that would go down here. They don't have to give you that if they give you the P, because if they give you phosphorus, then the 15 is guaranteed. That's what goes there. Okay, so they don't have to give you both. I could tell you the protons and you know the element, or I could tell you the element and you know the protons. So you do have to know that this is protons. You have to know what this is called up here. This is called the mass number. And it is the protons plus the neutrons added together. It is not on the periodic table. Okay, so that has to be given to you separately. You cannot find that from the periodic table. Okay, and then this guy over here, we've done a lot with since we first learned it. That's the charge. And how you get the charge is you take the protons and subtract the electrons, because electrons are negative and protons are positive, and that will give you the charge. So if I asked you, like I do on number 6, to give you the protons, electrons, and neutrons for each of these, you could say for P3 negative, the protons is 15. The neutrons should be 16, because we would have to take 31 minus the 15. The 31 is the protons and the neutrons added together. Okay, and then the electrons should be 18. And so how you can get that, you can get it a couple different ways. You can plug into what I just showed you. If you know the protons is 15, we don't know the electrons, and we know the charge is a -3, you can solve for the electrons have to be 18 there. Okay, or you can logic it out saying I know I have 15 pluses and I have to add, this means I have 3 more negatives than I have pluses. So if I have 15 pluses, I have to have 3 more negatives, or 18 negatives. Okay, so that would be for the phosphorus ion that's there. Alright, so if we go to the next one, so this is on question number 7, not 6. The next one said, alright, we're going to look at cobalt 59, so CO with a 3 plus and 59. So if we go back to the periodic table, the only thing you need to pull off the periodic table is the number of protons. So we were given CO3 plus with a 59. We can fill in the 27 down here. That's the atomic number. So if I asked you for protons here, you would say 27. If I asked you for neutrons, you would have to take the 59 minus the 27. So we would get 32. Okay, and if I asked you electrons, you would have to say 24. So you can either do, I've got 27 protons minus the number of electrons is equal to +3, and you'd get 24. Or you can look at this and say, hey, this means I've got 3 more pluses than I have negatives, and I know I have 27 pluses, so I have to have 3 less than that on the negatives. Okay, so there's your protons, electrons, and neutrons. Okay, so we'll go back and write that. So for phosphorus we had 15, 18, and 16, and cobalt we had 27, 24, and 32. Okay. Alright, so that is electrons, protons, and neutrons. Next up is the average atomic mass and the mass spectrometry. So that's there's an example of that later on in this review. It's oddly placed. It was a picture, so I need a little more space. So it's down on 24. It says, can you calculate the average atomic mass of the element in the mass spectrograph shown below and to identify the element? So you can do this a little bit quicker. You could probably find this element pretty easily, but I want to go back over how do you calculate the average atomic mass. So how you calculate the average atomic mass the same way we do your grades when they're weighted grades. So what you would do is you have all these different masses. You have 4 isotopes. So isotopes are simply the same element. They have the same protons. They have the same electrons. They just have different neutrons, which makes them weigh different things, because neutrons add to the weight. And so what you would do, you say you have an isotope that weighs 64, and it has a percentage. I'm just going to ballpark that and say that's 50%. So I'm going to multiply it by 0.50 because that's the decimal version of 50%. Okay, then I have an isotope that weighs 66, and I'm going to say its percentage is 30. And I'm definitely ballparking these, but we're going to talk about how you would know who this element is for sure. Okay, and then I've got an isotope that weighs 67. Okay, and then I'm going to ballpark that as, let's go with 3%. You could have something different. I'm just going to use 3% here. And then I've got an isotope that weighs 68, and I'll ballpark that. This one I have to be 0.17. Why I have to be 0.17 is whatever you pick as your percentages, they need to be roughly correct, but they also have to add to 100%. And so since I said this was 50, and I said this was 30, I'm at 80, and then I said this was 3, so I'm at 83. This guy has to be 17. So if you had picked a 4, you would have had to use a 16. If you had picked a 2, you would have had to use an 18 on that last one, or if your other ones had varied. Okay, and so you're going to multiply each of these. So this one's going to give you 32. This one's going to give you 19.8. The third one's going to give you 2.01. And the last one's going to give you 11.56. And I'm not really doing sig figs on any of this because I'm pulling these off, just ballparking them from the picture. And then what you're going to do is you're going to add all those together. So you could have written this a little differently and added them in one line instead of calculating them all differently, but just to show you what we're doing. Okay, so when you add these up together, you get 65.37. So that is the average atomic mass of this element. That is what is on the periodic table, that decimal number. And so if we got 65.37, we are looking for something that has the average atomic mass at closest to that. And so you'll find right here, zinc has an average atomic mass of 65.39. So that's how we're going to identify this element. The element here has to be Zn. So mine is a little off what they got on the periodic table because I'm eyeballing these numbers. There's not very good percentages. The other thing to make sure, in case you forget how to calculate this, but you can at least narrow it down, is the answer is definitely on the periodic table. So since you have to identify, it has to be one of the things on the periodic table, and you can tell that the answer, if you're going to average these, has to be between 64 and 68. And then when you calculate it, it should be closer to the 64 than the 68 because the 64 has the highest percentage. Most of this is 64. So just like whatever grade is weighted the most in your classes, so usually that's test grades, that's where your grade is going to be closest to. Whatever your test average is, that's what your overall grade is going to be closest to. Okay, so dead in the middle would have been 66 between 64 and 68, and we're definitely closer to the 64 in our final answer. And so if you went to the periodic table and you knew it had to be between 64 and 68, closer to 64, well, there's only one number that's between 64 and 68, which is this one. So you could have identified zinc to begin with. Okay, so that's mass spectrometry. Okay, going back to the outline, Coulomb's law. Earlier this year you were probably given a formula that looked like this, which made some of your hearts hurt because that makes you uncomfortable. But what you have to know about Coulomb's law is that it's about the level of attraction between two things. And Coulomb's law says the things that matter to attraction are the charge and the distance between them. So if I gave you a set of circles and said 3 plus 2 minus and 3 plus 2 minus there, and then 1 plus 1 minus there. All of these, if I asked you what they felt toward each other, what kind of force was between these two particles on each one, they would all be an attraction because they had opposite charges. They can all be attracted. If I asked you which one is the most attracted, you got to look at two things. So this law, even though you don't have to be able to calculate with it, says we're going to multiply the two charges. That's what we're looking at. Okay, so the multiplication of the two charges here is -6. Here it's -6, and here it's -1. Coulomb's law says you want that multiplication of the charges to be big. Big is good. Big is a strong force. Okay, and so then on the distance, if you're going to feel the force between them, you want the distance to be small. So these two guys, the first two, have the same charge multiplication, charge product there. Okay, but the second one has a much smaller distance between them. So this one's going to feel the biggest force. Okay, and then the one that's going to feel the smallest force is this guy. Okay, because the top and the bottom one, the blue and the green one, both have the same distance relatively, but their charges are different. The ones that have the bigger charges are going to have the bigger force between them. So this works not just if things are attracted. If you had two things that were both positive, they would be repelled. Okay, and so you would still have, it's about the size of the force, not whether it's attractive or repulsive there. It just says the size of the force is dictated by the charges and the distance between them. So the next up is about ion formation, and you do have some in-class things to look at from there. So going back up, we should be on number 8 now. Okay, it says what ions do the following atoms form, and to name each of them. And so this is where the periodic table kicks in. You just have to be able to find them. So you should remember, okay, get rid of all this, that we gave some charges to some families. That this first family is a +1. Then we have a +2. Then we skipped over all this middle stuff. We had a +3. We did not give this family a charge. We had a -3, a -2, a -1. And then the noble gases don't usually participate. They have a charge of 0. So what you do have to know is anything in here or down here, they can do multiple things. So they have multiple charges, with the exception of 3 atoms in there that we'll go back over. These guys can also do multiple things. Now the top 2 usually participate in just covalent bonds, so you don't see them with charges at all. But tin and lead down here especially, you will see them have different charges at different times, and you have to figure out what they are based on who they're with. But the main group elements that we're looking at, 1, 2, 3, and then -3, -2, -1. Okay, the 3 in this middle group, the transition elements that you have to know. You have to know those 3. You have to know that a silver is going to be a +1, and then cadmium and zinc are both +2s. Okay, so if you look back at that in-class review, it says what ions do the following atoms form. So if you look at the periodic table, nitrogen should make N with a -3, and we call that nitride. So the idea was if it came from the periodic table and we're making it negative, the ending changed to IDE. If you do B, if you look up oxygen, it should have a -2 charge, and we called that oxide. Okay, when you look up calcium, you should have a +2 charge. When we name it, we didn't change the name of our positives. We just call that calcium. Okay, aluminum, if we look it up, should have a +3 charge, and we still call that aluminum. Okay, and then the next one has a charge, because if you look up chromium on the periodic table, you'll find it right here. We don't know its family charge, so it can do different things. That's why you were given this charge. Okay, and so if you name this, what we have to say is not just chromium, we have to put chromium with Roman numeral 3 next to it. Okay, even though it's positive, it doesn't change its name, but we have to give Roman numerals. Okay, so that's ion formation. You're going to have to be able to predict those. Okay, then you got to know a little bit about the periodic table. So the next 2 on your outline, 20 and 21, are just knowing things on the periodic table. So first up is that you know the period numbers, and then the group numbers or names. So you're going to have to know what are periods and what are groups. So periods are this way. They're just numbered 1 through 7. So the other thing, groups, are columns. So they have 2 different numbering systems that you'll see. You see 1 through 18 going across, but you also see this A and B system. So the A's were the main group elements, and then the B's were called transition elements. Okay, and the B's are a little bit wonky in their numbering. Okay, so you do have to know that there are 4 columns that you need to know the names of. So you need to know that group 1A are called the alkali metals. Hydrogen is not part of this, doesn't belong. Okay, it's not a metal. So starting with lithium and down. Group 2A are called the alkaline earth metals. Okay, then you have to skip over to group 7A or 17. These are called the halogens. And then group 8A or 18 are called the noble gases. So you have to know those names. So I can give you them like an X and a Y coordinate. I could say, find me the element in period 4, group 15. So you would have to find period 4, group 15, and you tell me arsenic. Or I could say, okay, find me the alkaline earth metal in period 6. So you'd have to know the alkaline earth metals are here, and period 6 is here, and you'd have to say barium. So I can give you just a coordinate. So you have to be able to identify based on those. Okay. You need to also know where the metals, nonmetals, and metalloids are. So this little staircase is going to separate it for us. So hydrogen doesn't belong over here, but everything to the left of this staircase and down here, these are all your metals. Okay, everything to the right of the staircase and hydrogen. These are your nonmetals. And then the things touching the staircase, those are your metalloids. Okay, aluminum, you do have to know aluminum is a metal, not a metalloid. Okay, but most of this periodic table is metals. So that leads into the next thing that's kind of important, is you have to be able to identify metals for identifying ionic versus covalent bonds. So this next thing up on your in-class review is going to ask you about predicting whether things form ionic or covalent. So you have to know that for ionic, you're looking for a metal plus a non-metal. Or you're looking for things with polyatomic ions. Okay, and then for covalent, you're looking for non-metal with more non-metals. Okay, and then what we just learned in this last unit was if you put a metal with another metal, it's called an alloy. That's a mixture of metals. Okay, so we're not doing that, we're just doing ionic versus covalent, so you have to be able to find them. So if you look at question number 9, it says, can you tell whether each of the following contains ionic or covalent bonds or both? So we haven't mentioned that, so I'm going to definitely talk about that one in a second. But if you look at A, lithium chloride, LiCl, if you find lithium, it's going to be a metal, it's over on the left. Chlorine's a nonmetal, so we have ionic. Okay, B, carbon dioxide, CO2, both of those are nonmetal, that's going to be covalent. Okay, HF, H really belongs with the nonmetals, it's just over on the left side, so that's a nonmetal and a nonmetal, that's covalent. Okay, and so then when we get to D, this is a little bit weird, because here we have a metal and a polyatomic ion. So this is definitely ionic. However, a polyatomic ion, if you look at all your polyatomic ions, they're going to be in one nonmetal with another nonmetal. Okay, so a polyatomic ion itself is covalent. Together with the metal, we make an ionic. So this situation is both. It has both kinds of bonding. Okay, if you actually drew this out, you would have a K plus, and then you would have this NO3 minus. Well, the attraction between these two guys is ionic. It's positive and negative. But the attraction inside here that keeps the N's with the O's is covalent in here. Okay, those are all nonmetals in there. Alright, so then E, if you look at E, we've got polyatomic ions. We've got NH4 plus, we've got ClO4 negative. That's definitely ionic. But these guys itself are polyatomic ions. Those are covalent, so this is another both. Okay, so pretty much if you have your polyatomic ions, you're going to be both. And the last one doesn't have polyatomic ions. That's just a metal and a nonmetal. It's called ionic. Okay. Alright, so then last one on this thing is polar versus non-polar covalent bonds. So polar means that you're going to have opposite sides, essentially. So covalent meant that we're sharing electrons. Polar means it's unequal. One side has more electrons than the other. And non-polar means it's going to be equal sharing. So if you think about a tug-of-war between things, the only way that that tug-of-war ends up kind of equal is if the two sides are essentially the same thing. They're the same strength. Okay, so for atoms, we'll talk about it in detail later this year, but for atoms to be the same strength, they essentially have to be the same thing. If they're different things, then they're going to be pulling different and it won't be equal sharing. So in A, this is H fighting F. They're sharing electrons between them. Okay, this is not going to be equal. One side's going to win. You don't have to know who wins at this point, but this is definitely going to be polar. Okay, in the second one, in B, this is O fighting another O. Okay, and this is not the perfect drawing, so if anyone calls me on it, I know that's not right. But in general, that's O fighting O. If you're looking at that, you're not going to be able to tell any side winning. This is non-polar. No side is going to take more than the other. Okay, and then CO2. Okay, CO2 is like this. Okay, so this C is fighting O. So in this one right here, that's going to be unequal. That is polar. And in this side fighting the O, that is also polar. It's unequal. We'll talk about later this year as a whole what that molecule comes out to be. But generally, if you want to know whether something's polar or non-polar, by looking at the bond, you just look if it's the same atom, they're going to be non-polar. They're going to pull equally. If they're different atoms, they're not going to pull equally. And one side's going to pull more than the other. It's going to be called polar. Okay, so that's it for this section.